Hey, Jim. Hello, everyone, and welcome to our first Think Tank seminar of the 2024-2025 academic year. I'm honored to have Dr. Jim Thorson, Dr. Cole Monahan, Dr. Jane Sullivan, who's joining us remotely, and Dr. Juliet Shafagnac here, all from the NOAA Alaska Fisheries Science Center, where Juliet works in accordance with Dr. Andrea Hunt with her postdoc. And today they're going to be talking about their presentation of dynamic structural equation models as a novel framework for incorporating time variation into stock assessment models. So if you have any questions, whether you're in person or online, we prefer to have that go ahead during the presentation. So feel free to send a message in the chat with your question, and I'll go ahead and recite that to either Jim or Juliet, who will be the two presenting today. And if you're in person, feel free to raise your hand and they will answer your questions accordingly. So without further ado, I'll turn this over to Jim as we go ahead and start with our first think tank this year.
Yeah. Well, thank you so much. It's been a little while since I've done a think tank, and I'm excited to be here. I was sort of envisioning that people would have laptops, and so if anybody, I encourage you to get out your laptop. Yeah. Okay. Somebody, Jim, you got a lending library. Yeah,
I'm a lending off, but it's called budget spreadsheets.
Exactly. That's you get points for pretending to follow along at your laptop. So everybody just take a moment, get out your laptop if you want, go to your office, get your laptop. You know, that's the intent that, you know, I think of a think tank, but no worries if you don't have one or don't want to pretend. But yeah, and so we're kind of tag teaming here, and I'll try to stick to 40 minutes. So Juliet can have an hour and 20 minutes. I'd love to, you know, just have discussion as we go. Can we hear people off site if they, do we have to unmute, or you want to unmute everybody now and if you want to just shout?
So I will go ahead and unmute everyone online, and if you have a question, go ahead and shout.
Yeah, that's my preferred culture for this. So, I mean, maybe not the shouting, but you know, the intent of shouting with a normal voice. Yeah, so I'll say that I didn't have time to put all the pictures up I wanted, but I, as an undergrad, I remember picking up a Bayesian structural equation modeling book, and I think, you know, it's different people have probably run into structural equation modeling at different points in their career. You know, and then as I thought more about it, you know, there's this guy, Judea Pearl, who's been writing about causal modeling for decades. You know, he's gotten like philosophy awards for this. There's sort of a philosophical underpinning for a lot of causal modeling. You know, so like if you think about like the millennia of thinking about causality, like there's an expert in the philosophy department here who thinks about this. Like, you know, they refer to kind of our statistical modeling and causal analysis typically as like an instrumental theory of causality. And so, you know, Judea Pearl has done a lot of thinking about sort of like how you can think about causality as somebody kind of exogenously kind of doing something in a system with a bunch of interlocking variables. So there's you know, a couple decades of Judea Pearl thinking about kind of how to express in math sort of a philosophical thoughts about causality. And then more recently, I'd say, you know, Richard McElreath here in beard or no beard mode. You know, he's at Max Planck Institute. He's sort of the online face of, I think, this big bandwagon in statistics about causal analysis. So maybe some of you have seen statistical rethinking. You know, there's huge, you know, different science fields are doing this differently. You know, like I hear in economics that it's very hard to publish a paper if you don't have a identification strategy. You know, like if you're trained at UC Santa Barbara, you know, with Chris Costello, like economists teach about identification strategies. You know, social scientists have a way of doing this. In fisheries and ecology, there's a surprisingly little work on causality. You know, perhaps because we're just so used to doing experiments in microcosms and then just kind of hand waving and wildly extrapolating across a huge change in scale. But yeah, I think we're kind of late to the game and kind of catching up with the rest of science in terms of causality. And then, yeah, I mean, so sometimes if you read StatsLit, there's a third circle here, but you know, so sometimes people talk about like prediction inference and counterfactuals as different tasks that a statistician might have. But here, just kind of on a simple level, a lot of what we do as statisticians is kind of correlative modeling. So, exploratory regression modeling or supervised learning or splines. And so the idea of these kind of correlative models is that you can predict, interpolate between samples or predict something under constant conditions. So like, for instance, we're trying to do we've got this climate ecosystem fisheries initiative where we're trying to predict, how climate change might, changing water temperature might affect recruitment. And so the hope is that if we've got essentially kind of constant conditions, we can use a correlation between recruitment and temperature, and then read off the correlation to get a prediction under some different temperature. Causal methods, by contrast, are sort of a subset of statistics where you need a structural model. So you actually express the same thing using parameters that you think are constant over time and using mechanisms. Causal methods can be used to extrapolate beyond sampling or predict under changing conditions. You can kind of look, you could formalize this in different ways. So like, there's a chapter in my textbook that has a example about correlative models breaking down. I've been kind of publishing on this a little bit. Like, there was an earlier paper called the Grand Habitat Challenge where we published on sort of the need for structural equation modeling. But one of the more recent ones is this paper that, Alex Andrews is in Juneau, Scott Large is the branch chief at the Northeast Center Ecosystem Branch. Tim, everybody knows, and I'm assuming here, this professor at UW. And I'll say, this came out of a FATE proposal that Tim and I submitted in 2017, and at the time, I don't think we had a hard time explaining what we were trying to do. But yeah, essentially the goal of this is to come up, basically replace sort of a regression paradigm for doing modeling, climate-linked modeling, with this sort of structural modeling paradigm.
Real quick, Jim, would you mind getting out of presenter mode on your computer so other people online will be able to see the full screen?
Oh, interesting. So they're seeing my next slide, I guess.
Exactly.
Yeah, okay. So let's see. So how do I do out of presenter mode on the GoToWebinar?
You should just be able to do it on PowerPoint.
You should go to slideshow.
Oh yeah, that's the wrong one. So I click on slideshow, and then I get out of presenter mode here somehow.
Maybe display setting.
Display settings.
Yeah, it should just be.
Wow. Duplicate slideshow, maybe.
There we go. Perfect.
Okay, thank you. Yeah, so basically the goal of this exercise is to get to a kind of a structural model like this. So in some sense, this is like, there's sort of one way of thinking about this is this bridge from conceptual modeling to qualitative network modeling to dynamic structural equation modeling, and then to full nonlinear structural modeling. And so you could look at this diagram here and you could think that it's a conceptual model, so like the goal, one way to do this is to go in with stakeholders and have a bunch of people draw box and arrow models on a whiteboard, use that to elicit some expertise about how things are related to one another. And then you can go ahead and fit that to time series. Another way to view this is that by having a structural model, we have a better way of communicating what the model's doing, so this is like a glossy write-up of a model that, our comms team did. And so again, having sort of this box and arrow model, I think, everybody's done those sort of whiteboard jam set, people think, I think like this often about causality. And so this type of presentation is, I think, a good stakeholder engagement tool. Yeah, and then the other benefit is that you might have, you might be able to articulate different hypotheses about what's driving something. So Juliet, I think I'll get more into that. Or you might have different components of this that are non-stationary. So for instance, I don't know why it advances either. I've never worked out how PowerPoint works, but
Don't think anyone ever has.
yeah. But there's, yeah, so, in this case, the sort of standard regression paradigm would be that we've got sort of a team that has $1 million ROMS model. And so for them, everything's solved with a ROMS model. And so they might have sea ice going straight to a stock recruit residual. They're expensive. That is the point. And but then we've also got a separate team that goes out at the Alaska Center and measures copepods with bongo nets, and so we've been doing that for decades. And so, there's a separate team that has been doing a bunch of process studies of looking at how copepods might affect recruits, early life survival. And then we've got a separate team that goes out and does acoustic surveys for pollock, and then they realized, oh, we're picking up krill in our backscatter, so they make a krill index. And so you've got 3 separate teams. Copepods, krill, and physics are all correlated in the Bering Sea, where this diagram is showing. And so they end up all kind of arguing over which of those is the best index to use. And that argument ends up being a big issue at a center like the Alaska Center, where, whatever you pick, you're gonna disappoint other people, and there's pros and cons. And that's sort of where you end up with this regression paradigm for how to link things to climate, is you end up with a bunch, you end up with a multiple regression and an argument about a bunch of collinear predictor variables, where you just have to kind of choose one based on who you're friends with, or a bunch of model selection that doesn't work when you have collinear predictors. By contrast, in this sort of structural model paradigm, you can actually use expertise, ecology, to think about how things are related, why they're collinear, and use that to kind of solve what I think is a big organizational issue about how you integrate across multiple teams that are trying to get at these sort of climate drivers. So that's sort of the big picture of a few different perspectives on why you might want to do this. But in this case, what we estimate, and we can show the code for this in a minute, is we've got sea ice. In the Bering Sea, there's this polynya, where sea ice is ejected away from St. Matthew's Island, and because it's ejected away, there's water again at the surface, and so it's not being insulated. So it's this like ice factory, and that that is causing that winter sea ice creation causes a summer cold pool, really cold near bottom water. So that's shown there. So a high sea ice causes a high cold pool. When there's a big cold pool, we have a really strong link to copepods and a weaker positive link to krill. So a cold year has more copepods than krill in the water, whereas krill are kind of driven by something generally correlated with cold years, but not really that strongly correlated. When there's more copepods of krill, there's more copepods of krill in the diet of juvenile pollock in the fall surface trawl survey. And then when there's more copepods of krill in the diet, there's positive variation in the residuals of a Ricker stock recruit model for Bering Sea pollock. So on the right-hand side, we've got the spawner linked to log recruits per spawner. There's a Ricker model with a negative density dependence shown on the right. And in general, in the past, people would just they choose one of the variables shown on the left-hand side, even though they're all collinear. And they would test it and move on. Now we can actually do this sort of structural model for how, why these different predictors are correlated and how we can use them. So, so that's again the kind of big picture. Another way to view this is that I think we have this sort of missing middle. There's this sort of bandwagon about mice models, models of intermediate complexity for ecosystems. So basically, we have one group of people that does EBFM models. We do these big nonlinear structural models that only a few people can run, and we hire a postdoc to make one, and then we hope that they got everything right because it's impossible to review all of it. And then you make some predictions from it, and it only works. This strategy of structural modeling only works if you happen to get your nonlinear model exactly right. So if you've got something wrong in your nonlinear model, you're not guaranteed to get any useful causal analysis out of it. There's sort of another branch where we kind of do ensemble models, so we have a bunch of different sort of nonlinear models that we don't really know what they're doing, and then we see if they agree on something. And that's, that's sort of kind of, I'm satirizing it a little bit, of course, but, it's super useful work, but whether that actually gets at causality is sort of a difficult question. And then there's a separate branch of people, I think, at NOAA that do these process research studies. They do like simple studies, and they do correlations between one variable and another, and they kind of hope that they'll say that like a cold year leads to more copepods, and then another process study will do more copepods leads to better bioenergetics or better condition. Another person does a condition study linked to recruitment. They hope that if they daisy chain a bunch of these process correlations together, that they'll get the right answer. And that's kind of, it would be luck if you can daisy chain all this together and get the right answer, because there's a bunch of other drivers at each stage. So we're kind of missing a middle ground here, where we can test a bunch of, use our process research knowledge, but actually get it all synthesized together in a single model. So other fields do this in a bunch of different ways. I won't really get into it, but I'll try to speed up a little. Yeah, exactly. I've got too many slides here, but so one way to think about this is just an extension of linear models. So if you've got a simple linear model up here, you've got a response variable y and a predictor variable x. You've got some mean mu sub y, the mean of y, plus the slope beta times x, plus some variance delta that's normally distributed. So that top two lines is a linear model with a response variable and a predictor variable, and we all have fit that over and over again. We can augment that with a model for the predictor variable. So you say x has a mean and a variance and a different delta for the variation in x. And then once we've done that, we can write this whole thing out as a simultaneous equation. So we get the same expression back, where now we've got a zeta or z. This is the Andre and me for making up extra syllables in z. But
Go to Z, you'll be right.
Is that it? Okay, there we go. Z, there we go. So z is this sort of vector of the centered x and y, and epsilon is the vector of the two different deltas. And we can write out that top expression plus that augmented one as this simultaneous equation. So z is a path matrix gamma times itself plus this vector of errors, where the path matrix looks like this. So the original slope parameter from our linear regression is now an element of this path matrix gamma. But as we'll see, you can actually, this perfectly generalizes linear models, but it also gives you a bunch of other model structures. So yeah, for this one,
That would just be a daggy thing to do.
I wasn't going to show it, but I love using Microsoft Paint, but I don't have enough time. But yeah, it's just a box for X and a box for Y and a single arrow from X to Y. So each arrow will end up being a coefficient in this matrix gamma, and each box will end up being a variable in this Z, in this, and so the model, instead of a multiple, regression models have all these assumptions like exogeneity and independence that you might remember and nobody talks about again. So like a linear model only works if you've got these sort of specific assumptions. This gets rid of a lot of those assumptions and replace them with other assumptions.
I was going to say, it just changes the assumption.
It changes the assumptions, but yeah, you don't need all your covariates to be independent anymore, and you don't need them to be, the errors in your response don't need to be uncorrelated with the errors in your predictors, and so there's all these sort of ways that you can get a broader class of models. It reduces exactly to a linear model, but you also buys you a bunch of other model types. So walking through the equation a little bit more, so here I'm switching back from Z to X. So X times a path matrix gamma, X is the simultaneous equation with path matrix gamma, and epsilon is multivariate normal with this generalized covariance matrix. We can compute the expected variance of X as a Cholesky of this L, where L is this I minus delta inverse times the inner Cholesky covariance. So this is basically, we did this in the class I taught a lot. So you do this expression where you just subtract this across, and you get I minus delta equals this, and then you multiply that across, or you divide that across, which is the I minus delta inverse. So it's what's that? Oh, sorry, gamma. Yeah, the gamma, the path matrix gamma. Thank you. So so the variance of your simultaneous equation is this this sort of simple expression, and you can kind of derive it in a couple steps of linear algebra. And then the standard way of doing this, that people invented 100 years ago, like shoot, that fitness landscape guy, I'm forgetting his name right now. Doesn't matter. But the people who invented this, you can fit this as a Wishart distribution, which is sort of the variance of, like the variance of an estimated covariance matrix.
What was S on the left-hand side?
S is the sample variance of a set of your measurements.
Yeah.
Exactly. But you can also just actually fit it. I mean, that's the standard way that like an LCM software would fit this, is with a Wishart distribution. But we're not going to do that. We're going to kind of just stick with the general math that I'm showing here and fit it other ways. Yeah, I think I'll skip a bunch of this kind of adding lagged effects and how that goes through the linear algebra, and I'll just switch over to code. Okay, so here again is where having a laptop, I'd encourage you to follow along. So the code for this is this GitHub dsem here, and it's it's an R package on CRAN. So I'm kind of working on the dev branch at 1.4 right now. It's got this package down website, and so as we'll see, this dsem is sort of a tool where you could go in, you could start doing exploratory modeling. You could go in with a team. What we do at the Alaska Center is we'll have a team of people that are interested in forage fish, and we'll do a dsem for that. But once we've done that, we could then try to plug it later into a stock assessment model, and that's what Juliet will get to in a few minutes here. So dsem is software that allows you to do sort of exploratory modeling in a group setting. It runs in a second, and so you can do kind of iterative work as a group, and then eventually the idea is that you plug it back into the stock assessment model, or my sort of state space ecopaths with ecosim, or whatever model you're working with, or it's in TinyBass. This is the same interface that TinyBass uses. So yeah, so here's the package down. What?
Jim, I have a question. How many variables do you need to make this worth it? Like 2 or 10 or?
Yeah, I mean, with two, you could have X causes Y and Y causes X. You could have both arrows, but they're not both separately identifiable. And so you could fix one of them, or you could use a prior on one of them and then estimate the other one. So even there, you can do things with 2 variables. You can do things that you couldn't do with a regression model. But I haven't seen anybody do that. So like if you've got 2 variables and you've got full data, this will just collapse down to a linear model, and there's not really any need to do it. And then we've done it up to, I mean, I'm doing one where we have 20 variables, so I haven't really found, and it still runs in a second or something. I think this, So it's actually the same structure, the same model structure as input-output models. So if you've read about InPlan, this is the same model that they do. And, InPlan will fit models that are huge. So anyway.
Isn't huge one of the advantages?
Yeah, exactly. The goal is to make it huge. Yeah. So here's again my claim. So you could simulate X as a predictor variable, and then Y, where I've got a slope of 0.5 and an intercept of 1. I plug it in a data frame and I fit a linear model. So this is sort of the, I think a lot of people learn statistics in part by working through code. I mean, I guess that's how I think that's how a lot of people learn statistics in fisheries. You can fit the same model in DSEM. I mean, it's using the sort of tricks I've learned from STM, TMB, and Sean Anderson. I think he got it somewhat from Glim TMB, but so you've got these sort of extra control parameters in this function. Data has to be in this TS object. That's a time series. It's a time series class. And it's in wide form. This is a data frame, so it's got 2 columns for each variable. Now I'm just making it a wide form time series matrix. And then I write out the structural model is this. So, this is just an interface. This could be written out other ways too, but here I'm saying X causes Y with a lag of 0, and the resulting parameter is called beta. And so, yeah, I mean, I fit that and I get the same estimate and, well, very slight differences in standard error, between a linear model and a DSEM. So, and then you might wonder, oh, well, what about, residuals and so forth. So here I'm doing these leave one out residuals, plugging it into Dharma. This is the DSEM residuals in Dharma. And then, I plot it against working residuals. This is working residuals from the LM package. And, you get the exact same answer. So working residuals are equivalent to LOO residuals. Cole and I've talked about other types of residuals, and I don't want to get into it too far, but you can collapse this down to a linear model, you get the same answer. You can then do more complicated models. So this is a Klein model is an econ model for macroeconomics. It's like a simple model that this guy Klein, I think, got a Nobel Prize in economics. And so here you can express this Klein model as a series of 3 dynamic linear models. So consumption is a function of profits, corporate profits, plus the lag of corporate profits, plus the same slope for private wages and government wages. Investment is a function of corporate profits, lag to corporate profits and capital stock. And private wages is a function of GNP, gross national product, the lag of GNP, and time. And so DLM is a package that allows you to do these lagged effects easily in a linear model interface. You can write the same model out in a DSEM, this using this block. So this is sort of the interface. And so I'm saying corporate profits affect consumption with lag 0, and that's parameter A1. Corporate profits affect consumption with a lag of 1, and that's a different parameter A2. And then here you can mirror parameters. So you could say private wages affects consumption with a parameter A3, and it's the same slope that you're estimating for government wages affecting consumption with A3. So this interface is expressive, is like a machine learning term, where you can write out, a bunch of, you can write out a DAG where each of these arrows is an arrow in a directed acyclic. It doesn't actually need to be acyclic. You can write out, it's more general than a directed acyclic graph because you have cycles. But you're specifying each arrow and you can fix them at the same value. And you could also, if you wanted, you could fix some of them at a known value. So if you wanted to, if you want to test, some experiment, that estimated a slope here, you just name that parameter NA, and then you put another comma in the value after that. And so you can turn off parameters, you can mirror them, and then we've got a bunch of model selection stuff that might be helpful in some contexts and is probably not helpful in other contexts. Yeah, so this model so this is all of the specification, and I like this format because it's, you know, it's expressive, it's pretty clear what you're specifying, I think. And yeah, so then you just pass this text file, you know, this string, and it parses it. You give it the TS object. Here I'm telling it to estimate deviations away from the equilibrium. Yeah.
Just on the expressiveness, you shouldn't read those as assignment arrows in R, right?
Correct.
So,
Yeah, I'm sorry. And so this is forked off of this interface that John Fox wrote for the SEM package. John Fox is at McMaster. There's a, you know, it has this SEM package. There's a separate package called Lavon, which is the more widely used SEM R package that has a different interface. We actually write out things with a tilde notation. So you could write out your actual, kind of like you do in JAGS, you could write out your actual tilde notation for the model. And so somebody could, I mean, I don't think it would take that long to just take the Lavon interface and use that instead. It's all the same model. It's just waiting for somebody to write the code, you know, take the code from Lavon onto their license and, you know, plug it in here. So, yeah, so, and then I'm just doing, you know, I'm trying to show that I finally learned ggplot. So yeah, so I mean, here's the data and here's the ggplot, you know, comparison of this ordinarily squares for the DLM, you know, the DLM package against this. I'm calling it GMRF here because it's the DSEM is actually a big Gaussian Markov random field. Or you can show the DAG here, and then I think I'll just stop. Maybe I'll show the Pollock one, and then I'll stop talking. But here's a DAG showing it. So this, you know, it's estimating all these, you know, each of these arrows corresponds to a thing that we specified up here. So, you know, we said time goes to private wages with lag 0. So time goes to private wages, but now there's an estimate. So there's a 0.13. And then private wages goes to consumption with a value 0.8. And so what this model means is if you, that's a bad example because time, nobody's going to do a counterfactual time travel. But okay, so let's go look at GNP. If you've got a change in GNP, like if you, let's just try to make this a good example. So government wages is going, it's,
No, we're good through December 20th.
yeah, I mean, like if you had a supply shock, like hypothetically supply chains made everything more expensive and corporate profits went down, that would mean this model predicts that would cause a decrease in investment. And then this tag is not showing me what the value of investment to consumption is. But corporate profits, because of a supply chain, is going to affect investment, and that's going to affect consumption. But it's also, corporate profits has a direct effect on consumption for some reason that I can't remember in the Klein model.
trickle down.
Yeah, totally. Yeah, and so the point is that if you want to figure out what happens if you change corporate profits exogenously, like if a policymaker changed taxes or something, didn't do anything else, it would have an effect on consumption via this direct effect of corporate profits to consumption, but it would also have an indirect effect of corporate profits on investment and then on the consumption. And so the total effect is this plus the product of this estimate and this estimate. And I wish that this graph was showing what this value was, but yeah.
So if I'm reading the STEM text file correctly, there's like an effect. Private wages and government wages are sharing this like A3.
Yeah.
Is that like an interaction effect, or are you constraining the effect to be the same between?
Yeah, I'm constraining it to be the same. Exactly. So that's okay. So this, yeah, thanks for reminding me. So private wages to consumption is the same as government wages to consumption. So this is estimated 0.8. And then there's kind of a 0.8 you can see here. And then I think it's overwriting some investment to consumption thing that I can't see on this graph, the way it's plotted, but
I think the invest just happens to be on the path.
okay, that makes sense. So I would say one of the bigger problems with this is like the automated software for plotting the output. And then I think both of us have wrestled with that stuff, but yeah, okay.
Jim, you've got estimates with standard errors.
Yeah.
What, does the concept of model selection really exist within this context? And if so, how do you do model selection? Can you use sort of standard model selection? Basically, at what point do you say a number is sufficiently small, you can basically ignore that link even if a whole bunch of experts say it's definitely there?
Yeah, model selection we could spend a whole seminar on, I'm sure. I think that the short answer, why don't we just table that? I think there's,
Well, we're gonna talk about it. Julia's gonna talk about it.
Yeah.
A little bit.
I don't even think we are on the same, it's just too new for us to have gotten on the same page about how we want to talk about it.
Can you go back to the fitted DAG? One point I wanna, maybe it's not clear is, and McCalry talks about this a lot, like, the arrows are an assumption, right? The causal structure in the system is not in the data. It's something that we make, it's an assumption that we make, we impose it. What's statistical about it is once we've imposed the structural equation model, the SEM, the DAG, that we estimate those parameters from the data. So that's the statistical part.
Sure, but the question in some sense is, well, my question, I guess, is why isn't there a link between GNP and consumption? Why? You've excluded it a priori, right? You've said it can't exist, so you can't estimate.
Well, you're fixing it at zero.
You're fixing it at zero, exactly. And so sort of that goes, and I can assure this is what Juliet's going to talk about, but in most of these sort of little pictures on the board, you come up with multiple alternative models of the system. And, ideally you want to be able to say what's the relative likelihood of Jim knowing what's going on with Paula. Okay, to some guy this is great in the sense that if you know what your system is, this estimates the parameters conditional on that. But if you get the arrow, if I left the direct arrow from C profits to consumption out of this model, not that it's a very big link, presumably the data will splice the effect, that direct effect, somehow into some of the indirect effects. So it sort of goes to you made a point earlier that if you don't get the model right, things don't work.
Yeah.
And then you talk about DSEM, sort of implicitly indicating that you solved that problem. But in fact, I think you just transferred the problem into a new version of the same problem.
Yeah, exactly. I think that's true. So there's caveats on that though. So for instance, like you can do an omnibus test on rejecting a model. So like if in this structure, this says there's no direct effect of GNP on consumption conditional on private wages. And so if the residuals of this model show that the residuals of GNP are correlated with the residuals of consumption in a way that's statistically significant, that is an accept reject test on this structure.
And you have a sense of the power of that?
People do it all. In other fields do that.
Economics, they've got too much data. So.
Well, this is only 20 years of data. So I picked this because it's similar to ours, but yeah, I'm not an expert on this. Partly this is sort of a, call to arms bit about like, let's read up on what about a third of statisticians do, which is causal modeling.
And I would argue that we don't know the structure of any of our stock assessments.
We know the structure of the stock assessment, not the stock.
Yeah.
We
don't know the system.
Yeah.
I think of this as it's an improved framework to test different assumptions that are derived from things we think we know. And right now we don't have a tool to do that. So it's a step forward, but it's, as Juliet will point out at the end, it's a big hammer and we need to learn how to use it properly.
How do you avoid spurious?
We'll get to that.
Okay. Yeah.
Just in general, how complete does the data need to be in the time series? Like if you have a bunch of missing stuff on one variable, or they're at different time steps, can you only include something where it's complete at every time step?
So it jointly deals with missing data. And so, going down to the Pollock one, here, can you ask that again in just a second? Yeah, so that, oh, Jesus. Oh yeah. So here's what you're looking at. So this is the specification for that Pollock example that we saw, the kind of glossy comms version of. So, log sea ice affects log cold pool extent with a parameter. Log cold pool affects fall calenus and summer euphousins.
With a lag of 0.
With a lag of 0. This is, and then euphausids affect creeks responder. Yeah, I mean, you can read it yourself, but, and then this is the block of AR1 parameters, so there's sort of this, like Myers and Honig, and there was a bunch of papers in the 90s about how if you test for recruitment correlations and you ignore autocorrelation of residuals, you get, anti-conservative tests, which people have subsequently ignored. And then, there's actually a whole field of economics called co-integration, so like prices have a random walk structure, and there's a bunch of like stock market goes with a random walk on that. So this is a generalization of co-integration models that Nobel Prize for Economics a couple of years ago went to somebody doing those. So that, this has good coverage, statistical coverage, even if some of the variables have a random walk, which is not true of multiple regression. And so here we're just allowing it to estimate ARs as a way of avoiding that anti-conservative autocorrelated residuals issue.
And that helps with smoothing if you're missing data. You put AR1, it'll fit a late state in between, so it can't handle missing data.
Exactly. So here we've got the imputed missing values. So copepods and sea ice, I guess, are probably not highly autocorrelated, but like fall calenus, we've only got a biological survey when we have enough money, like pocket change and a couch, and so we've got these really broad confidence intervals between points, but it doesn't balloon out to the full variance because it's got this autocorrelation. It's kind of, so one way to view this is, and I've got a vignette on this, is that it's sort of a generalization of dynamic factor analysis. So DFA, you can make this into a DFA model, and DFA is sort of a way of inferring sort of what's the dominant trend and then trying to impute missing values or whatever.
So I missed it. In this case, going back to the linear model, the X's have an AR1 process underlying them as well as everything else.
Yeah, exactly. That's the choice I made in this setup.
Right,
I specified it to have that. But yeah, and so like I'm doing this on the Arctic IERP with Libby Lagerweld right now, and we have a bunch of different, some of those variables are 2 samples, well, we've got 4, but then the variance is so big that we kick out a bunch of them. So, when we do, in that case, we're doing model selection, and if you've got very few samples, they just drop out, model. They drop out of the model when you do stepwise model selection. So, so there's sort of a model selection story about missing data that we could get into. Okay, so that's, and then here again, I mean, I think this should be the same values, or it might be that the comms team made the plot with a slightly earlier version, I forget, but, and here's the p-value from a 2-sided Wald test, I don't know, but, yeah, so there's other kind of versions of it, like DFA or a vector autoregressive model, or kind of site replicated time series that we get into in the vignettes here, but, I think that's as far as I wanted to go.
I think one thing, maybe we'll do that, switches over. One of the really cool things about it I like is that it lets us scale from a linear model to really complex models all in the same framework.
Sorry.
So, and that's, Juliet will show some examples where we've tested some different things, but for sarcasm context, normally we just have a regression and we input our covariate as known and estimate a beta. That's a correlative relationship. But we can scale, and she has a really nice figure of this across a huge range of kind of different model structures, all within the same framework. And that to me is the really exciting part from this, from a stock assessment perspective. It's not like we have to code our assessment in some econ programming language and they would have no way to compare it. It's like, no, within a TMB model, we can scale from, what we currently do, nothing, IID, all the way up to, 100 variables from an ecosystem in a causal framework, which we're not proposing to do, but like in the framework, we can do that.
Well, I mean, I'm trying to do two things at once, but nonlinear relationships, given the interest in threshold effects and stuff like that, you ready for that, or did I just mistake?
So yeah, the short answer is no. You can do a nonlinear version if you're willing to go back to a DAG. So, if it's, the caveat to that is actually this can do nonlinear if you have full data. So if you've got a covariate where you have every measurement, you just do this line based expansion and put those in as multiple columns, and then you can just do a nonlinear effect. But the nonlinear doesn't play well with the missing data. Is the
There's computational role and theoretical.
Yeah, exactly. So somebody could write code, and I've done some anyway. Let's put a pin in that.
And while they're doing this, can I just say, this is highly experimental. Like, she's barely 6 months into her postdoc. We don't have all the answers. This is a think tank, so we're trying to get feedback. We're not claiming we've solved a bunch of problems, but we think it's a tool that we can use to try to solve some problems and answer some interesting questions. So we're still working it out. So just keep that in mind. It's definitely in progress.
Is there anybody on the
Can I ask a question?
Go on.
Hey, Jim, it's Mark Warner here. Can you hear me?
Yeah.
So basically, you've gone over in general dynamic structural equation models and things like that. The question I have, and we've discussed this before, is how does this differ from what we currently do, and what advantages are the systems you're talking about? Is it basically just efficient ways of estimating the parameters of these models, or because a lot of what you're talking about is things that we already do kind of maybe in an ad hoc way, or we use some of them but not all of them? And I'm just wondering if what you're presenting is really not much different to what we do, and we just need to really put it in a formal context so we're all talking in the same language or using the same methods.
So I think that's close to fair. I think it gets us to a place where we're doing what we think we're doing. Right now we put in covariates, and that's the regression paradigm is what we do in stock assessment. Throw SST into your regression on whatever. But like if you intervened, if you wanted to ask the question, like what if SST was higher? You can't actually do that in a regression framework because it's not causal, right? And so, but we interpret it that way a lot.
That would do it. I mean, that's just projecting beyond what data you have. I mean,
but if something else is causing two things, and you increase one, it's not going to drive the other one.
For me, the difference, firstly, is in the measurement error of the covariates. I think that is a fundamentally different thing. Sorry?
Both. We should. Can we punt this, because I think Juliet's going to cover it.
I get to override that, given what you just used.
Please, yeah.
And my answer, Mark, is that I don't know. I think every time we have a bunch of people that are putting temperature into stuff, and temperature could increase or decrease almost everything that we talk about. So like temperature might increase growth rates if there's enough forage, or it might increase starvation if there's not enough forage. And so temperature almost never has a direct and stationary link on what we want at the scales we're talking about. So I don't know anybody in any stock assessment model that's actually done a model that looks at how temperature is affecting the proximal. Temperature is the distal cause, but there's a bunch of proximal causes like predator-prey overlap, or consumption, or consumption over metabolic demand. that are the actual mechanisms.
Separate from things like cold pool effect on fastest.
Yeah, I mean,
Because that's observation, that's more of a.
yeah, exactly. Even that, the goal of science is to get as mechanistic as you can. And so, you can start with this correlation, and then you just, as a scientist, should always figure out what's the intervening things between it. And, that's what this allows you to do.
Yeah, and I guess that's what I'm trying to say in the context of star assessment. If we say, oh, well, if we think SST is going to go up 2 degrees, we take our regression and we project it out, like, we don't know that,
Well, how much do you know in DSM if you've got the DSM wrong?
We don't, but it's at least a statistical framework that's designed to answer those questions. That's fair, right, Jen?
Yeah, I think so.
To put this in context, one thing that Rick and I did with Delta Smelt was we projected the model, and it's a bit like the fishery impact plots. We projected the model in the past with like average conditions rather than the conditions you actually had in terms of temperature and other covariates, and determined what the effect was on the actual population in the past. And we also did it simultaneously with and without the effect, so we could estimate the uncertainty in that effect. Is that the same thing as you kind of talking about here?
So again, I would say if you've only got a predictor and a response, who cares? Do a linear model. But like Delta Smelt, it's not just temperature, but it's like people are going to be asking you about how much they diverted water.
Yeah, so all included as well. Yeah, we looked at alternative covariates.
Exactly. So you did a multiple regression where you tested different covariates, each having a direct effect on something. But it could be that water temperature is actually driving diversion. And so, it could be that they divert more water when there's a high, when it's a warm year because they're fighting fires with it and people water their gardens more or something, And so you're not going to get the right answer if you're testing different covariates, each with a direct effect, if there's a relationship between your covariates.
I think that really is the difference.
Yeah.
I mean, if you only have direct effects, I think it all, apart from measurement error, probably comes out in the wash. But once you've got the indirect effects, I think that's one. We certainly don't deal with in any of the regression type approaches that I see. So none of the covariates always impact the response, not the covariates impact indirectly through those
other covariates. Exactly.
And we often have research that tells us how they interact.
Right.
And so it's a shame to throw that information away.
In the open soil model, we have timing, temperature, and the interaction of the two.
Yeah.
Right, that's not indirect. That's not the indirect.
Yeah, in that case, like what I think would be useful is like, they're moving inshore because of age structure or I don't know. I don't have a good example for that one, but.
Given we've got an hour.
Yeah, let's go.
I guess Juliet gets to go, but yes, we may need another thing packaged.
We have one more quick question from the chat. If you go back to your DSM package, there are 0.001s next to your autoregression equations or.
Oh yeah, I'm sorry. So I'm not going to replug stuff, but I'm in the interface, I'm giving it starting values. So another thing that the interface allows you to do is just give it starting values. And I forget why I did that in that vignette, but if you have a parameter named NA and then you have a value after it, it's the starting value is the next number after the NA and it's turned off. So it just stays, it's fixed at that starting value. You can also give it a starting value and estimate it.
Thanks.
Okay, I guess I'm good to go. So welcome to Think Tank Part 2. I'm trying to explain how we're using the dynamic structural equation model developed by Jim to incorporate climate information and time variation into stock assessment models. And that's work I'm doing for my postdoc here with Cole, Lauren, Rogers, Andre, Kelly Shotwell, Jim Sullivan, and Jim. So I'm not going to detail why we need stock assessment to help our fishery management and why we need our fishery management to have sustainable population. One of the challenge we currently have in our stock assessment model is to account for productivity change within a stock. And there is mostly two ways of doing this. One is like two current way of doing this, let's say. One is to add some stochastic variation in a biological parameter or population process within a model. So using what usually we are calling a random effect. So let's say you have a process P, which is represented here. You could use an IID model to represent it. So you just think that he has a mean and he has a deviation around that mean to model its variation across time. And another model which is quite used is the autoregressive model. So here I'm presenting order one, but you have a bunch of order. So you're just adding autocorrelation parameter in your prediction of the process. So here are that's that's a panel of methods which are quite used nowadays in the stock assessment models to account for some productivity change. Another way of doing it is to estimate an explicit link between the population process and some unvolatile variables. So here you can have your process, you have one or two external variables that you're usually also smoothing with an IID or an R1 process, so estimating parameter for them as well, and you're saying that they have an impact on your population process. So that's the two methods which are usually used, and what's available for that inside a stock assessment. So when using stock synthesis, you can do that, but you cannot estimate your sigma parameter, so you have a penalized random effect. And if you want to use a smooth curve regression, usually you're going to smooth your variables outside of the model and not inside. SAM, so stock assessment model built by Nielsen and Berg in DTU, is also using the IID and R1 method to allow some variation around their population processes. I don't think they have included the eco regression yet, and one which has been developed on the East Coast at the Woods Hole Institute allows those three approaches, I'd say, and that's the one allowing the smooth eco regression more extensively than stock synthesis is doing, like in a full state space approaches where you can estimate both process error and measurement error. So that's what we have now, and the new approach Jim has presented with the DSEM, actually, dynamic structural equation modeling, allows us to go beyond that. So I had here what the model can do. So you can have a bunch of variables and you're inferring what are their structures, so if they are R1 or IID, and you're also inferring some causal link between them and infinite to the process. So you can see here I'm saying that A has a direct link to P, but C has an indirect impact through B going to P. So that's, I think, something we're talking about, like a distal versus proximal causal link. And what we claim for this approach is to be quite flexible, so you really can go from an IID model to something really more complex like this with few lines of code. So it's the SEM expression that Jim was showing before. We just like write what the relation, internal relation of the variables and what is the causal relation they have. And you can do that easily. And I will also add that you have a lot of flexible option for your input data, so you can deal with missing data. You can deal with different family of time series, so some Poisson, some you have normal family. I think you have Gamma. I don't remember. You have a whole bunch of family handled there, and because it is state space, you can also model the era around the observation within some period, but it's possible to do it. So that's the approach we developed with DSEM. So the idea is really to couple the DSEM model and the stock assessment model. Technically, we kind of copied and paste Jim's TMB code inside our assessment TMB code, and with some modification, it worked. So the idea to couple them, that's you have your two models, the stock assessment with all the usual stock assessment data, and your DSEM model with the time series. You're making your hypothesis on the internal and external link they have. Jim presented his matrix calculus, and you're minimizing the likelihood, and then you're getting the parameter estimation. So what's the smoother of the time series and what are the link between the different time series. And you have also, because of the time series model, you can forecast your data. So, and the causal link between them is also forecasted. So when you couple them globally, you're mixing all of this, and what we have to do is making your hypothesis on the causal link between the variables and with the population process. And then globally, you would have your stock assessment data are gonna pull your process, like your process which are random parameter are going to be both informed by the stock assessment data and the environmental time series with the causal relationship. And then your outputs are all the parameter and your forecast for your environmental time series, and also the process you were looking at. And now the process is informed by the causal link and the forecast time series. So that's the broad idea of what we're doing, and I'm gonna give more detail on the case study we're doing now. Yeah.
Question, because well, firstly, I sort of like the way you're going and integrating the two into one, and I'm not sure who I'm asking this question to, but I saw with the Pollock you had SSV as one of the covariates. And of course, SSV is really not a covariate because it's a model output, whereas what you're doing is where SSV is coming in, it's internal to the calculation, obviously, because the SSV is being computed inside the model, which is why I actually like the integrated version rather than the draw the bot model and then ask Jim, can I have the SSV time series, which you then treat as a covariate with observation and all sorts of weird stuff. So yeah. I was wondering to what extent you guys have thought about that. I'm assuming you agree with me that integrating it makes much more sense than taking it outside the model in the first place, but any thoughts on that? Because I think that is one of the big advantages of what you guys are doing, is that you're integrating the process understanding and the stock assessment simultaneously, rather than treating stock assessment output as if it's data. And then you have to deal with Liz Brooks, and we all know how that ends for most people. So we don't want to do that. Most of the skin is regrowing.
That was the other Pollock.
Yes, we're not dealing with that here.
Yeah, and that was the paper. I mean, I'll field that one unless you want to.
I mean, just to say yes, Andre.
Yeah.
All of it.
The short answer is yes. The long answer is like almost everything that goes into assessment is model output. And there's actually a trade-off here of like, the more you integrate everything into a single model, the fewer people who can actually access it. So I would say in practice, we actually need a continuum here where you've got simple to use things that we can easily talk about and we can have stakeholders do. And that's the role for DSEM on model output. You know, we're not going to bring in a bunch of stakeholders to run a fully integrated stock assessment model. And, you know, so I don't agree that there's sort of only ever the goal is to make everything a big integrated model, because then we'll just end up, I mean, it's a full employment strategy. I understand as a professor why it's a good strategy to maintain, but yeah. But, you know, I actually think we need to maintain a continuum of sort of simple and model output to integrate it.
Are you going to talk about that, like what we call the external one at all?
No.
Yeah, so maybe just to clarify that point, this is internal. So in our case, we have recruitment. There's no information in the covariates about recruitment. All the information in recruitment comes from the stock assessment data, the age comps, et cetera. And so you can take the estimates of recruitment from your assessment and just pull them out of the model and stick it into what we sometimes call an external DSEM. And that can be used to work with people. But I think that's valuable, but integrating it in is clearly the best approach from a stock assessment perspective.
So if you have a poorly informed recruitment but a really good relationship, it's not going, the right-hand side here isn't going to affect the recruits.
No, it's doing shrinkage both ways. Yeah, I mean,
We'll show some plots which might help with that. So maybe we should move on. But yes, in the whole novel bit of Juliet's work is to embed DSEM into a stock assessment. Sure.
So case study is the Gulf of Alaska pollock, so not the same one that Jim was presenting before. It has a custom stock assessment model in TMB, which was very practical for the purpose of our approach. We're focusing here on recruitment, which is defined at the age 1 fish abundance. I'm plotting here it on the right. And you can see that, you can see on the plot that the hypothesis for the forecast for the stock is just a mean. So that's something we're gonna look at for our results. And you can also see that you have a lot of variability in the error estimation, recruitment estimation. And for this stock and for some of Alaskan stock, you have what you call the ecosystem socioeconomic profile, which are available, which are like a whole data set with a lot of diverse ecological and socioeconomic variables that I'm going to show here for the Gulf of Alaska pollock. So I'm kind of so we have, I think, 25 variables. I'm categorizing them in different groups. So you have some predators or competitors biomass, some physical variables, wind, temperature, heat wave index, some biological variables, mostly collected by survey. So some abundance of prey, so index of condition for different stage of the fish, and some spatiotemporal indicators. So all this data set is collected through a lot of different monitoring systems and pulled in the ESP report, and they have been selected because they have an influence on the stocks, and here we have a way of directly integrating them. So so we have this ESP data set. The next step was to.
These are all data, they're not like model outputs, like ROM model.
Not some of them.
We're not using those right now.
I'm more concerned about what happens if you start to descend ROM's output for multiple variables, which are themselves actually functionally related because they came out with the same model. But I can't read the captions. I can barely read ESP data set. To what, I mean, again, this is not Juliet. So people will say, physics, it affects more physics, but if the physics all come, the data all come from a ROMS model, there is not just a functional relationship, it's arithmetic.
Yeah, I mean, we do that all the time in other stuff too. I mean, I do think it's important, but I'd say it's a second order. You do. So like every time you review EFH, you're reviewing a bunch of different habitat features.
You don't know my opinion on EFH.
I do know yeah, I know, but unfortunately you do have to stand behind the SSC work.
I usually don't, I'm not in the room when we review EFH.
That's okay, exactly. We all have a weak defense on this one, but
I mean, just for the sake of time, maybe we're saying, I think it's a very valid concern, and we're not doing that in this presentation, but that's something we need to sort that out as a field for sure. Agreed.
Okay, so then with the help of the ESP people, we came with a full causal map. So what's the process knowledge about the stock things are the variables affecting recruitment. So you can see here that there is a lot of causing variables and a lot of errors between them. And there is so we have this knowledge about what are the link and which link are positive or negative for them. But we start with that, but we cannot model all of this. We need to simplify this map. And what we choose to do for simplification is not just dropping some link randomly and compare what gives a better AIC or stuff like this. We try to use all the process knowledge and the process research and the expert knowledge we have gained through the ESP process. So we use our stock specific indicators. We came with a first causal map that we reviewed with some experts. They help us identify some improved data set, and we refine the candidate causal map. Then through the DSEM stock assessment modeling, the coupled modeling process, we are fitting those candidate map. We are making some diagnostic, making model selection, looking at what are the most important driver we are seeing for the stock, and looping back, so showing them the maps which are working the best, talking with the expert about, is it a good thing? Do you think we're missing something? And looping back to a model exercise again. So that's how we think the causal map development should be done. And in the end, we also think that the results we're getting from the causal map and from this modeling can help prioritizing the ecosystem monitoring and the process research. So that's how we consider the thing in an idealistic development of ecosystem causal map within the stock assessment framework, and that's what we're aiming to. More specifically on that stock, we've been moving with several causal maps, which are simplification of the first causal map I showed you. So we start with something pretty simple, and then we try to add some predators to that. We finally decided to add some condition index to the mix, and the map here is the one we are working with now. So now we are in the results section. So that's what comes out of the model. Jim showed you those kind of plots before. So we have for all of the time series of the variables, what are the link between them? So we have, so maybe I should get a precision on that. That's the hypothesis of the causal form we are getting in the model. We say we think that those variables are linked this way. We're not saying anything about the positiveness or negativeness of the link. We're just saying we think there is a link, and the model estimates them. So, and we also have like the p-value giving us like the significance of the link. So you can see that here most of them are significant, and Mostly this was consistent with the expert knowledge of how the system should work. We mostly have a concern here with that link saying that the condition of the juvenile offshore young of the year has a negative relation with the rec day. I didn't precise. This is recruitment deviation, so which is linked to the overall recruitment then. So that's where we have the link to recruitment. And this negative link between condition and recruitment is counterintuitive, and we haven't fully understood what's going on
Are you
here
sure
yet.
it's not the other way around?
What do you mean?
Let's call on Kelly, because she has her hand up.
Sorry?
Let's call on Kelly, who raised her hand
Oh,
politely.
sorry. I'm not very good at politely.
Is sigma R being estimated in this model?
Yes. And we're going to show results about that in a minute.
Do you want to ignore my question as well?
I don't remember what it was.
So yeah, I guess one thing it's maybe we wasn't like some of these are lagged, so that's like
Yes.
you know the age 0 fish how healthy were the age 0 fish last year? You think would if they're really healthy and fat, there should be more survival, so there should be more. So we have the opposite sign. So some of these are lagged and some of these aren't. It just depends on the covariate, right?
We still need to work on the plotting things because for now we see everything as the same. But yes, mostly this link is lagged. So this is all on the same year, I think, and this is lagged, and those are lagged too. So that's our estimation of the causal link within our system. And what we also get from the model is the recruitment estimation and forecast. So in blue, you have the model where recruitment is not informed by the causal map. So we're still feeding the causal map internally to be able to compare our model, but there is no link from the causal map to the recruitment. So there, it's our model, but with no link in the middle. So this is equivalent to a usual stock assessment model, and I'm not showing it here, but this would have the same recruitment estimates exactly than the usual stock assessment model. And we're comparing that with, so I'm calling this model Air IID, and because the recruitment just have his IID property, and the other model is the Air DSM or DSM in pink here, which is where recruitment is informed by the causal map. So which correspond to what you saw on the slide before. So you can see that you have some slight change in the recruitment estimation in the past, and mostly what differ is in the future. So for your Air IID, you're reverting to the mean because that's the hypothesis you're making in the forecast. And for RDSM, you have your estimation, which is a bit different. And I'm not projecting very far in the future, but one of the property of the model is that after some year of projection, it's going to revert to a mean because we have our smoother on other time series, and we don't have on our projections. I didn't see.
Yeah, so the only reason those are different in the forecast because of the lag effects that you're estimating, the red and the blue line.
Yeah, you have something with the lag effect. Yes, because you have all the information of the causal map of the causal map modifying your recruitment estimation.
Near term outlook.
Yes.
So if you had no lags, you would revert to the basically you would revert
But not
to
that.
the
But still with a lag, like it won't revert directly to the mean because you have your smoother on the
But the
time
smoother
series.
is because it has a lag in the smoother.
Yeah.
So I think, and then the caveat I'd say in that, if you're interested, is that you, like you could have temperature, like net measured temperature be the like thing at the top of it, but you could have a ROMS model be correlated with that. And then you could have the ROMS model actually out in the future, whereas the net measured temperature. So
that's where I was going.
exactly.
Yeah.
Yeah.
So use part of that causal map where you have data to look in the near term future.
Yeah, exactly. If we've got near-term forecasts or end of century or whatever, we could put that in the graph, and that, even with no lags, it would still be doing some informative thing. And And then you could also take it a step further and say that the model's doing a type of delta change method. So like it's doing a really simple form of delta, like people get into those delta change methods to intercalibrate ROMs and net.
Right.
So anyway.
Okay, cool.
Have you tried, can I ask a question? Have you tried just an AR model? So like the historical recruitments are all very similar, which is not surprising. There's a lot of data going in. And it's sort of the current and future recruitments that are different. And it looks like the RDSEM model could also be produced by just a simple AR1 model. Have you tried that?
No, not directly, but we could compare that to the AR1 model. But we, like, the causal map is significant. Like, we have multiple significant links, so that's also informing the recruitment forecast, I think.
Well, yeah, but it's significant, sure, but if you're like, I guess this is a really complicated model that took a lot of effort to put together, and if you're giving the same advice, like at the end of the day, if the management advice is the same, it's just a simple AR1 recruitment model. That's, I think, noteworthy, even if there are significant terms in this complicated model.
So I've got a little soapbox I'd be happy to get on. I feel like a lot of assessment people are trained in this sort of Walters lineage, where like we think of like assessments mainly being about harvest control rule advice. But like assessments are actually a big social construction that communicate to a bunch of stuff. And one use of an assessment is that prioritizing future surveys. And that's most of what the council works on, I think, is not the harvest advice. It's like, top 10 research priorities, or closure areas, or writing letters to commerce about declining survey funding. And so that sort of, understanding in that beautiful graphic you guys had about how DSEM links back to process research, it might not differ in harvest advice, but it could differ a lot in terms of other decision making that's using the assessment. We're just trained by Carl Walters to ignore everything except the harvest control rule.
I would say practically we're using a lot more for advice than for survey prioritization or funding research, like looking at where things go.
If you quantify more by how much it's talked about at the council, I disagree. But it depends. Yeah, there's sort of a hall of mirrors at the bottom of science prioritization about what we think is important and what's not. And a lot of us in assessments are trained to think the harvest advice is the more important thing.
Can I?
Long discussion.
Yeah. I mean, I want to say a couple things. Kiva, you're absolutely right. And I would say that's the real advantage of this framework, is that we could directly compare IID, AR1, and these different causal maps. I don't know if Juliet's tried it, but when a very long time ago, the very beginning, we did try it. I don't think we have any results here though. But that's kind of the point. And I also don't want people to get hung up on this one case study. This is supposed to be a method development. I think it is interesting to look at some examples, and it's possible that an AR1 would have a better AIC in this case, and that maybe would be better to be used for management. But I think it's really interesting to look at the causal maps and learn something about the system. And I agree with Jim that it helps us think about what is important to measure about the ecosystem if we want to understand recruitment of the stock, which we get back to at the end. But yeah, Kiva, it's a good insight.
I mean, the other side of this is a data-rich stock. You're not likely to learn about recruitment by more Pacific Standard, maybe not. By the rest of the planet Earth. I mean, this is, so in principle, some of this stuff, if you've got the right covariates, can actually inform the data poor parts of the assessment itself. And this assessment, if you look at the recruitment, they're really not very different historically from the actual assessment. So you're not learning a lot about history. But if you've got maybe 1 year, whatever that is, 2015 seems to be a little different. But in principle, when you've got a data poor assessment, you're actually, the auxiliary information may well be quite informative, assuming you can tease out the relationships for part of it, particularly for stocks where we go back further than 1970, where you might have environmental variables, but you wouldn't have a lot of age and size content, for example.
Which is not the case here because most of our ESP data are
Very short term as well.
yeah, and are starting really later than all the HCOM data. But
I was actually thinking of things like Cal Coffee and stuff, which go back decades before we've got good fishery data, at least in Southern California.
Yeah, like where the shrinkage is improving precision will depend on your data availability.
And we need a tool to test those scenarios. And so that's the point of this seminar, is to present the tool.
Well, I think the other point that you're making is a good one. It lets decision makers know the value of the information and the data sets that they have. And in a funding constrained environment, which we all seem to be entering, it says if I can collect 2 out of 3 data sets, which 2 is it going to be? That's basically what we just did for pollen, right?
Is it though? Because I think you're taking Jim's argument that we're kind of missing the point. I think if I was a manager, I'd say, yeah, stop doing any of this. Doesn't matter. I mean, of that fancy stuff, the tools.
Can we let her finish the results? Because I think it does, I do think it matters, and I think she can prove it.
Well, Julie wants to get a job, and that's her.
Well, before we go on, we do have a couple of questions from the chat, if that's okay, to keep the questions rolling. So first, have you tried a retrospective analysis to see how or whether the DSIM relationships might be changing over time? And are there other ways you can test for non-stationarity within DSIM?
yes, we've been working with, so I'm presenting some of the retrospective analysis. So yes, you're gonna see some of that.
That it seems like it's difficult to test the set of a priori assumptions surrounding the specific causal structure of the SEM. Do you think this might lead to issues in settings where there exists deep uncertainty about how experimental results collected at smaller scales scale up the whole systems? And he guesses SEM places a lot of reliance on the experts getting it right. Is there any guidance of what exactly we want to do about that going forward?
I mean, the way I'd say it is like, even that we can talk about this is a step forward. Like it's not going to solve uncertainty as like structural uncertainty is a problem, but it cues up that as a problem and makes it very obvious. And so I think that we have that same thing we're doing all the time when we take temperature and put it in as a covariate. There we're just kind of hiding it behind a correlation. And we're doing it in a way that just sets up a bunch of organizational conflict because there's a bunch of other teams that are studying the process drivers. So this sort of solves an organizational issue and it cues up it focuses attention on the actual problem.
And this is one of our big discussion points at the end. So let's get through the results. Thanks, Jim.
Yes, so we can also look at the estimation of sigma R, which is estimated in the ARID model around 1. I mentioned earlier that it was quite high. And within this model, it's reduced to 0.55 something. So you have a big variance reduction, showing that you are explaining an important part of the recruitment variability with inferring this causal map. So that's for the recruitment part. As Jim showed before, you also have this temporal property of the model. So you are actually filling all the missing data of your initial time series. And so that's what I was talking about before. They are quite like the black point or the actual data. And so compared to the assessment time frame, where like the ESP time series are relatively quite short. And what I wanted to show within this plot is because of the causal relationship and because with the DSEM model we are making some assumption between the causal between the ESP part and the stock assessment part, you can see that you're not estimating the same past of the variables with the two models. So in other terms, you have an impact of the stock assessment estimation on your ESP variables, which is quite surprising for like when you haven't seen that before, I'd say. And so the fact that when it's in the past with a part we don't have data about, I don't think it doesn't matter that much. But what can happen, I'm not showing it here, but because we have some measurement error around, we can have some measurement error around our data point. You can also have that the estimation for a certain year is not passing through the data point. So you are changing, in some way, changing what you have been observing because of the stock assessment model. So that's something we're calling aliasing.
Aliasing.
Ah.
I think, I don't know, Tim Miller uses it in WAM. I don't know if it's elsewhere. It's a normal thing.
Okay. Then I'm getting to, comparison with other causal maps. This is missing some lines in the plot, but that's okay. So I'm just comparing the AIC we have for a bunch of other causal maps we've been exploring. So the maps I'm talking to you today is this one having the lowest AIC, and it has a better AIC. That's something which was way more complicated, which way more causal links and way more variables in it, and it also has a better AIC. That's something which revert to a regression, so we would just have like adult condition, SST, wind direction, and condition of the juveniles informing the recruitment. So which is, maybe that's a lot of variables for a regression, but that would be what one could use to put some environmental covariates into a stock assessment.
If I could do a 30-second tangent on this point about model selection, there's, this is marginal AIC, and marginal AIC tends to favor more complicated models. And there's a new conditional AIC that, I published a kind of shitty version of this year, and people at Memorial have a much better version that we hope to get an archive within the next 6 months or a year. So, so conditional AIC will probably favor slightly simpler models, but based on our testing so far, but won't radically change it.
Yeah, we can see if that selects the upper right one or not.
Totally.
Can I also just point out, these are actually comparable. So if you take one of all of the variables are in all of the maps. It's just when they're not there, the links aren't shown. So the AICs are comparable. The data are the same.
Okay.
Just to make sure that, I'm sure Kiva was going to ask about that, which is a good question. So yes, they're comparable. Okay, go ahead.
And I'm also making a comparison within, for each of those maps, what the model without the link to recruitment, the causal link to recruitment would be. So what is the AID model comparison for each causal map? And you can see that we have a big gain of AIC for using those causal link to infer recruitment for all of these models. Next step is the model validation. So we'd like to see if our model is wrong. So are we making bad hypotheses about the data? Are we, do we have bias in our parameter and derived quantity estimation? That's some things we have done or are working on, and I'm not presenting that today. The other question is the model useful? So is the actual causal map improving the recruitment prediction? So we're talking about the predictive performance of the model, and for this I'm presenting some 1 year ahead prediction, retrospective prediction. So these are the time series of the data. So I already said that the real time series are quite short and a bit sparse. So a lot of those time series are actually like a survey which goes at 1 year out of 2. So you have like a lot of missing points in that. So we've been doing some exploration with real time series data, real data time series, and other one with what we call idealistic time series. So we are using the model capabilities to simulate the time series of the environmental data to see what would be the results in recruitment forecast if our time series was complete. Like if we had something going back really earlier and not that much missing. Oh, we're on time. Okay. So for the idealistic case, so this is the technical side of how we're doing the skill testing. Because we coupled the model, but we still have some hurdles with the complete match of them. So we have to do a lot of steps for this predictive skill testing. So the broad idea is that we have our RDSM assessment model. We are estimating, so that's our conditioning fit, which we are calling the operating model. This is estimating XTJ, which is the matrix of estimated recruitment of ESP and recruitment latent state. So the matrix with everything estimating, what I was, like the plot I had two slides ago, I think. Using this XTJ, we are fitting an external DSM, so just Jim's package, usually, with our input time series for the ESP, which is in the matrix called YTJ, and we are giving the recruitment from the latent state we are estimating before. And with this, we can simulate new latent state, XTJ star, and new observed data, YTJ star. Then we build our RDSM stock assessment model with this XTJ star. So that means that we have a new environment which is driving a new recruitment, which is driving a new stock dynamics, so new stock assessment data, which here I'm calling Z star. And then I'm doing for PPLs, trimming our observation data, so stock assessment data and ESP data with some years, fitting a conditioning model with this trim data, so a model matching what was your operating model and a non-matching model, so which is the opposite. So if your operating model is a model with a link between the causal map and the recruitment, that's the same, and the other one is no link between recruitment and causal map. And then you compute your root mean square error. So you have 2 EM. We are making some repetition of that, not that much for now, but that's what we'll make a lot of them then. And 2 OM, so the one where recruitment is driven by the causal map and the one where it's not. So here is what we are getting for one repetition. So you have your black point, which are the true recruitment for a type of OM. So you have the OM with RDSM and the model with IID. So you have different recruitment for them. And then what is the matching and unmatching EM is estimating to be the recruitment forecast for different pills. Each color is different pills. And we're forecasting 3 years in advance. So for all of this, we can compute a difference between the true recruitment and what is estimated by the model, and compute a global root mean square error. So that's what the global results is. So I'm summing over repetition for each pills. So, and the color is what OM you are using, and what is shown is the difference of RMSE between the matching and unmatching EM. So if you have a negative value, that means that your matching OM is doing a better job at predicting recruitment than the unmatching one. So you can see that for the RDSM model, it's the case. You mostly have negative values, and the average of all of this is a difference of 28%. For the AIID operating model, so when you don't have a link between recruitment and the causal maps in your simulation, the difference between your matching and unmatching estimating model are quite small, and they are differing between peers. So that's saying that in the end, if you are making a bad assumption about this link, if it doesn't exist, the model doesn't make such difference in the predictive scale. That doesn't make a lot of difference in the predictive performance of the model. So this is for 1 year, and for if you project 2 years and 3 years, things are not getting that good for the RDSM model, so you're losing some predictive power when you, for the 2 or 3 years of projection. We haven't really understood that why yet, but, and we haven't project really further as well. So that's something to explore later.
I mean, is there a bunch of, I mean, are there lag 2 stuff, or is just the 2?
No,
Okay.
there is only like 1.
Yeah.
So that's probably also what's happening.
But if the correlations are high on the covariates, then it should work for 3 years.
Yeah.
So it's going to depend a lot on the
values.
the conditioning model, the values.
Technical correlation, the covariates.
And also, I think you might have quite difference between the pills, because with some of them you're losing, when you're getting back, you're losing a lot of the data for some ESP variables, so that might have an impact as well. Let's get to the real data type of predictive skill testing. So you don't have any operating model anymore, you only have your 2 estimating model, and we're using the estimated recruitment in 2023 as our true recruitment, which is arguable, but that's the best estimate we can have, and we're computing same RMSE for HPIL and EM. So that's the result we have for 1 year projection. So we are just computing the difference between RDSM and AIID. So same negative values show that you have a better predictive performance for RDSM. So for 5-year pill, you have a 23% of difference, and when you are going back higher back in time, you're kind of losing a bit of this power. And same pattern when you're projecting 2 and 3 years forward, you're losing, like you don't have such a good predictive power. But that's a good point, that it can be linked with the lag in our causal relationship. So yes, that's what we have for the predictive skill testing. We also, I'm thinking about that because we mentioned that someone mentioned in the question, we've been looking at how the causal link change when you peel some year back, and you have some differences. And we had like, for the real data, we had like a pivotal year in, I think it's pill 7 or pill 8, where the estimation of the DSM parameters were changing a lot when you were peeling back. So that's something we are looking at as well. And that's my conclusion slide. So the coupling of the assessment model and the DSM model works, which wasn't something we could be sure before trying it. So that's nice. We have some significant causal link. We reduce the recruitment variances, so we are explaining something. There's a good self-test behavior with no bias in the estimation, and it's very quick to run. Do you know how quick is your model to run normally? 1.5 minutes something.
Yeah, maybe a minute, maybe, yeah, adds a minute or time maybe.
Yeah, it has like less than a minute to run time, so it's quite quick. In terms of predictive performance,
Oh, yeah, we're gonna be on in 5 minutes. Unless you want to try to faculty meeting.
I have a real.
Yeah.
On the last slide,
this one? No, Sam, this?
yeah, the previous one. Just, root mean squared error is prediction relative to what got estimated, whatever, right, next year. And I guess, would it be worth looking at something like a containment? Because in the original figure of the recruitment, the uncertainty in the projection year was about the same for IID entities.
Like look at coverage, like how often
I
it's
don't
within
know
the
how
confidence
you
interval or
do the
something.
computation, but, I mean, yeah, it was clear that adding something, the thing where there's a relationship and having lower recruitment that's predicted due to the lags is great. And that seems to explain some of what you're finding here, right? Or it's related to it. And I just wonder, like, you have more information, you're adding, it's fitting. Of course, I think you would expect to have better performance on root mean squared error. But I guess I'm wondering about the uncertainty, if that's something that's working. Because we really haven't reduced uncertainty very much from what I can see.
We have all, we could test, we could do coverage calculations, yeah, we could test it.
I mean, but awesome stuff.
Works.
Yeah.
Publish it before it doesn't work.
It's an easy way. Like using the causal map stuff, I show this AIC plot where there is really a better AIC that's using like just a regression method. We should test what the difference with just an AR1 model, which is a totally valid question. And our predictive performance depends a lot on the length and completeness of the ESP data. And what I mean by stock property is what is your sigma R like? It's like having a change in your sigma R is driving a lot what your predictive performance is. Yes.
Do you have any ideas for linking the DSEM model inside of an assessment model to something other than recruitment deviation?
So yes, that's something we would like to test. It's coming in one slide. So we are thinking of trying to link to multiple processes within the same stock assessment model. So maybe mortality, natural mortality, or growth, or maybe cacheability.
In some sense, if you committed to this approach, every random effect in your assessment model would be in the DSEM model component, not in the assessment. So that's how you would structure your model. So it'd be anything you want to put time variation on would be in the DSEM component. And it can handle them all simultaneously.
So one sub-thread of that is, like instead of doing Matt Cheng's like triple separable selectivity smoother, you can do something really similar with the DSEM notation to express that same thing. So, it gets away from all of, SS. Stock Princess has all these different special case interface for different things that are, and you can do all of that more or less with the DSEM notation.
We have a question as to whether the comparison test should be against traditional covariate testing, treating each of the covariates independently rather than a causal map.
I didn't, can you?
Yeah.
Like doing each of them individually in model selection or something.
Yeah.
Like, so instead of on your graph where you had the 4 going in like multiple
Yeah.
regression, I think they were maybe saying just do single univariate regression and model selection or something. I don't know.
Yeah,
There's
you
also-
mentioned that.
Yeah, and Eric just published that Fisheries about doing DFA on all your covariates and plugging that in and that being the best performing. I mean, there's, that also you could do in DSEM.
Yeah,
but
that's
so
something we're aiming to go to, trying to integrate. So you have Jim has his GFA functionality working in the SEM. So we'd like to try to do that in the couple assessment DSEM model to see if that's working, because it's an alternative of when you have good expert knowledge guiding you to build a good causal map, you can also try that.
But just on this, like Kelly, your question there, see there's two P's on the right side. So that could be growth mortality, and you could have temperature affecting both causally. So you can do kind of whatever you want. It's super flexible.
Yeah, so the take home is flexible framework, which is resolving the regression paradigm. So we're going beyond that. It's a good path towards the next generation of climate-linked assessment model, and that's a direct use of the ESP data and all those data, and which, in our opinion, can allow some feedback regarding the data collection and process research. And the general thing we're going to look in the next month would be like, we'd like to test the sensitivity to causal map misspecification in a simulation case, I think, and maybe look at how it comes with some other model misspecification. Maybe looking to integrate that in a stock assessment platform for broader dissemination. That's something which is possible. And there is also a global thinking to have about the workflow and good practices regarding causal map development, which remains to do. Yeah. More perspective, but we are a bit out of time, maybe. I don't know.
Yeah.
Are we?
Yeah, given that there's a faculty meeting here in a couple minutes, yeah, we're just about out of time. So if there's any last quick questions, feel free to ask. If not.
And if there is not, you can still reach me for more information or question, and I acknowledge my co-authors, all the ESP contributors, which build this data set, which is very useful, and my funding. Thanks, everyone.
So thank you again to Jim, Juliet, and Cole, and Jane Sullivan, who was online today for giving this. Next week, Andre will be giving. Yeah. 2 weeks. Yeah. Not to give you a heart attack. In 2 weeks.
It will not be as polished as this. In fact, it may be quite short.
That's part of the fun.
Although we can have a really interesting session about budget spreadsheets.
Yeah. So thank you everyone for joining online as well.
Presentation on why our studio is too hard.